Okay, so can you see the screen?
Yes, sir.
Okay. So that is the current mirror circuit that we introduced in our last class. Right? It has two transistors, right? So the two transistors, the Q1 is call it the input side, Q2 is considered to be the output side. So in Q1, we establish a current. Here it's denoted as IR. And then that current is reproduced in Q2, right? It's denoted as I naught, also known as the output current. So the current in Q1 is reproduced in current in Q2. So that's why it's called the current mirror circuit. So let's write it. This is our current mirror circuit. The IR that we can easily determine, that's VCC minus VBE divided by R. Right? So that is the current IR. And since these two bases are tied together, so they have the same, will have the same collector currents. IC1 will be equal to IC2, provided that AE1, the emitter, is the cross-sectional area of transistor 1 is same as the transistor 2, right? So they have the same cross-sectional area. Then the two collector currents will be same. As we also mentioned in the last class, the collector current depends on the saturation, right? IS, the saturation current, and the base to emitter voltage VBE, right, by VT. So if VB, these two bases are tied together, so they have the same VBE. So as long as they have the same IS, the IC will be same. And IS will be same if the cross-sectional area is same, right? If the cross-sectional area is different, then we can also calculate the currents from this relation. IC1 by IC2 will be this, equal to the ratio of the two saturation currents, and that will be equal to the ratio of the two emitter cross-sectional areas. Right? And so that is how the collector current is related to the emitter cross-sectional areas. And assuming that two transistors are identical, IC1 will be equal to IC2. And if we ignore base current, which is usually much smaller than IC, then IR we can equate to IC1, right? IR equal to IC1, and that IC1 is reproduced right in Q2, that is equal to IC2, and IC2 is same as I naught, right? Same as I naught. So that is how we get the IR I naught, right? So current that we establish in Q1, so that is reproduced in the second transistor. So that part is clear, right? Any question on this?
No, sir.
That is what we have already discussed in the last class. Right? And now we said that if you want a different amount of current, then you just change the cross-section area. If you want a larger current, take a transistor with a larger cross-sectional area. A smaller current, take a transistor with a smaller cross-sectional area. So if you want, let's say, I naught to be the twice of our IR, that reference current, then the cross-sectional area of transistor 2 should be twice the cross-sectional area of transistor 1, right, AE1. So in that case, in the diagram that we usually denote by just times 2, right? Times 2. So if you see this times 2, then you'll understand the cross-sectional area of this one is twice the cross-sectional area of Q1, and current here will be twice the current. If you want current to be 4 times, right, you denote by times 4. So that means the size of this one will be 4 times the size of Q1, and you will have current will be also 4 times. So that is how there is one way to indicate. And there also another way to indicate this, that another way to indicate this is to just draw another transistor in parallel. So draw another transistor in parallel. Right? Let's say call it Q3. Right? So that bases will be tied, shorted all the bases. And assuming they have the same cross-section area, so the current here will be IC3. Right? Now, when you draw like this, we assume that they all have the same cross-sectional areas. So we have IC1 equal to IC2, and that is equal to IC3. They're all same, right? So I naught will be the twice of these two currents, and that will be 2IR, right? So that is another way of showing. So if we have 4 transistors, then the current here will be 4 times of this current. Is that clear, guys? That is how to show, the size of the transistor with respect to the first transistor and the corresponding current that will flow, right, in this second transistor or the transistor in the output side. So by controlling the size of the transistor, we can easily control or adjust the amount of current, right, that will flow in the output side. And another aspect of this one, we also mentioned in the last class that we can reproduce this current as many times as we want. And that is very useful when we have a multi-stage amplifier. And usually integrated circuits, we have many stages, right? And so that becomes very useful. Just add one more transistor here and you get another current source supplying another current to another stage, right? So let's call it Q3. And let's say this current here is I01 and current here will be I02. Right? So this current will be supplied to one transistor, one stage, and then this will be supplied to the another stage. And if we need different, usually we need different amount of current for different stages. Let's say the current here we need twice as this one. So you can indicate that by times 2. If current here we need 4 times of this one, we can indicate that by times 4. And so on, and we can increase it to as many times as we want. They will have the same VBE, same base to emitter voltage. Any question, guys? No question. Hello.
Yes, sir. No questions, sir.
Okay. Okay, so let's show this multi-stage differential amplifier we had discussed thoroughly. Yes. Okay. Yeah, hold on a minute. So that is our multi-stage differential amplifier. Now we need to supply the bias current to this differential amplifiers. Before we showed them with this current source symbol here. Now we are going to use the actual circuit, right, that will supply the bias currents, and that we can show like this. So here Q5 is our main, the current source transistor that will produce this current I, and then this current I will be reproduced, right, in Q6 and Q7, right? So if the voltage drop here is VBE, right, then I we can write as VCC minus VBE, right? And then we have minus VEE, so minus it becomes plus VEE, and that divided by R, right? So that will be the current. So by adjusting this value of resistance R, we can set the current as we need, right, which is suitable for us. Let's say this current is 0.5 milliampere, we want 0.5 milliampere, and here we want 2 milliampere, right? So a little bit lower current to have high input resistance, and high current, bias current to have high gain. So now this this current we can set as 0.5 milliampere, right? So then this will be reproduced here, same if they have the assuming same cross-sectional areas, right? But we need a higher current, so we have to use a transistor with a higher cross-sectional, larger cross-sectional area, let's say times 4. So then it will be current I2 will be 2 milliampere. Is that clear, guys?
Yes, sir.
Okay. So go to next. This is so now we have discussed the concept of the current mirror circuit, how they can be used to bias the transistors, the amplifiers. Now we discuss about the performance of the current mirror circuits, how we evaluate the performance of the current mirror circuits. The performance of the current mirror circuits are determined by these two factors, gain and error. And what are the sources of error? There are two sources of error, the finite value of beta and finite value of R naught. So before we understand this, let's need to define, right, what is gain and what is error. Okay, let's do that. Now in the our earlier discussion, we said that this Q1 is our input side, Q2 is our output side. And so this side, the current here, we denoted IR. IR stands for reference. And also we can also denote this as the input current. So that we can call I in. I in the input current, and this side is our I out, the output current. And then we have this voltage here is VBE, right? So this we call the basic current mirror circuit. Now, ideal situation that I output current should be equal to I input current, right? And then we define the gain as it is defined, the output current, output get by input, right? So that is the gain. So output by input, that is our gain, and that should be 1, right? But that is the ideal situation, okay? Ideal case. And how the error is defined? Error is defined as the actual gain, sorry, actual gain minus the ideal gain, the difference. So that is defined as the error. So actual gain we can get by analyzing the circuit, and that we write as I out by I in, actual output current divided by actual input current, and the ideal gain is supposed to be 1, so minus 1. So that is defined as the error, right? So these two parameters, they, are used to evaluate the performance, right? The less is the error, the better is the performance level of the current mirror circuit. And there are two sources of error that causes I out output current to be different from the input current. Those two are the finite value of beta, the current gain, and the other is the finite value of the R naught, the output resistance of the transistor. Right? Ideal transistor should have infinite R naught. The transistor working here like current source. An ideal current source should have infinite output resistance. But all practical transistor will have some finite value for the output resistance. Is that clear, guys? Any question?
No, sir.
Okay. So we'll discuss individually how these two factors causes the output current to be different from the input current, and what is the error due to each of these factors. So first we will consider the finite value of beta, right? How it introduces error in the circuit. And this is from the very simple fact that the base current in the transistor is given by IC by beta, right? So what happens, you have a base current flowing here, right, IB, and you have another base current flowing here, IB, right? So, and the current that will flow here will be 2IB. Right? So, and the current here is our IC, right? The collector current. And in previous discussion, we ignored the base current. We ignored base current. We assume IC1 is equal to I in, right? I in is equal to IC1. And then since they have the same base to emitter voltages, both the transistors, So that IC1 will be same as IC2 and IC2 same as I out. So that is how we followed this, right, path, right, tracing the currents. And I in is equal to IC1, ignoring the base current, right? And then IC1 is reproduced as IC2, and IC2 is I out. So I in is equal to I out. So see, we ignored the base current, assuming this is zero, right? And it is zero only when this beta is infinite. Beta is infinite, then IB is zero, and I in is equal to IC. But beta is not infinite. We have finite value of beta, so IB will not be zero. So there will be some non-zero current flowing here. So I in is basically summation of this IC1 and 2IB, right? So that is how the I in is different from IC, is not same, and that our initial assumption was not uh, completely correct, right? So there will be some difference, and there will be an error in the current mirror circuit. So let's try to find out what will be the error because of that. We can write now that I input current will be equal to IC1 that plus 2IB, right? Now IB is IC by beta, right? So this one we can easily write as IC1 plus 2, IB is IC by beta, so IC1 by beta. And then we can write as IC1 times 1 plus 2 by beta. Since the bases are tied together, so they have the same base to emitter voltages. So these two currents will be same. Assuming that these two transistors are identical, they have the same emitter cross-sectional areas, right? So IC1 equal to IC2, and so that will be IC2, 1 plus 2 by beta, and IC2 is same as the I out, so we write I out 1 plus 2 by beta. Okay, so we got an expression, right, or an equation that relates I in, the input current, to the output current. And so we can write now the expression for the gain for this current mirror circuit, which is defined as the gain is equal to I out by I in, and that is equal to 1 over 1 plus 2 by beta. Is that clear, guys?
Yes, sir.
Okay. So what you see from here, that gain is not exactly 1, rather it is less than 1, right? Our gain here is, it is less than 1. Gain is less than 1. So output current will be less than the input current, right? Because output current is equal to IC2, and IC2 is equal to IC1, right? Not equal to I in, and I in greater than IC1 by the amount of this base current, right, 2IB. So now what will be the error? So the definition of error is output by input, sorry, the actual gain minus the ideal gain. So actual gain here 1 by 1 plus 2 by beta, that is our actual gain, and minus the ideal gain, which is 1. And if we do the math, so what we get 1 plus 2 by beta, and here we have -2 by beta. So that will be our error in this circuit. Now, usually the beta is much larger, right? Let's say about 100 or something. Right? Then we can assume that in the denominator what we have, right? The 2 by beta, in the denominator, this 2 by beta, since beta is large, will be much smaller than 1. So this part will be much smaller than 1. So we can approximate this to this we can approximate to -2 by beta. Is that clear, guys?
Yes, sir.
Okay. Error is negative, as you can see, since the output is less than input. So we have a negative error. Right? So it shows that the output is less than the input. And okay, so let's take a typical example of how much error can be. Let's say beta is 100, right? If beta is 100, then you see that error will be -0.02, right? If you convert in percent, so that will be -2% in terms of percent. So the error will be 2%. For larger beta, error will be less, and for if beta is small, then error gets larger. So if transistor with the higher values of beta will give a better performance, right, as a current mirror circuit. Now, here we have just one transistor at the output side, but in integrated circuit, let's say we have a multiple stages, right, and then we'll have multiple of these output multiple of transistors, right, at the output side supplying currents to multiple stages. So if you have one more transistor here, Q3, then what will be the error, right? Let's say this is I out 1, then you have I out 2, right? So what happens in this case, you have another transistor. Then one base current is going to the base of Q2. The another base current will go into the base of Q3. So we have another IB here. So now the IB here will have 3 IB, right? Now the I in has to supply the base current to the bases of 3 transistors, right? So on top of IC1, it also has to supply 3 IB, right? And how the equations will modify now. So now here you will have IC1 plus 3 IB, right? So there are 3 base currents, and then this will be also 3. This will be also 3. This will be also 3. So this will be our modification, and then here also we need to change. So that will be our 3 by beta. So gain will further reduce, and so will be the error. Error will go in opposite direction, it will increase. Right? So here, we can change this, right? So now error here will be 3 by beta minus 3 by beta and minus 3 by beta. For beta 100, it will be minus 0.03. Error will be 3%. Is that clear, guys?
Yes, sir. Sir, the base current going to the Q2, won't it be twice IV?
Q2. Q2
Yes,
will
sir.
take only one IB, no? And then Q3 will take another IB. Right? I mean, basically, this is connected like this, right?
Okay.
Right? It's not the same line. They are different connections. Right? So to look it more, not that clumsy, so you draw it like this. But one node branching out, right, to 3 bases, to the input of 3 bases.
Got it.
Yeah. So similarly, if you have a more number of stages, so here you have 3 transistors in this current mirror circuit. So if you have n number of transistors, for n number of transistors, so what we'll have, so we'll have n IB, right? This is supplied to the n transistors. So replaced by n, all the numbers. And then here also 3 will change. So that is n. Okay. So write n here. That will be gain. That will be error. As n by beta much smaller than 1. N by beta, and that will be n, right? N%. So, any question, guys?
No, sir.
So what is the conclusion here?
As the number of stages increases, the error also increases.
Right. So error increases with the number of transistors, number of stages. So that is a problem because usually we have many stages, and so the error will be quite large. So that is a problem. So how to overcome this problem? Now coming to the solution part of this error. So there is a solution to every problem, but not every problem we have solution yet.
So we have to reduce the base current that is coming from the Q1.
Coming from Q1, is how do you reduce that?
That I don't know.
Okay. The error we are getting because the IN has to supply, right, the base currents, right? And how do you reduce the base current? You can reduce by if you have high value for beta, right? Because IB is IC by beta. If beta is large, so then we can have less base current, right? So that is one way, but that is not that easy, right? There is a limit to that. We cannot have infinite beta. We can always have some finite value. So there is some limit to that. So there comes your creativity, right? How innovative you can be, right? So you'll see that we have some very interesting concepts, ideas, right? To solve different problems in the circuit. And throughout this century, the electrical engineers are, I think, the most innovative ones. Right? They have come up with many different ingenious solutions to different problems, and that are now used not only in electrical engineering but in all branches of engineering and also in medical sciences.
So we connect
Yes.
for here
What?
current buffer.
Current buffer.
Yes, sir.
How it will help?
So it will provide the necessary current.
Current buffer is used to transfer the current.
Okay.
Yeah. Like voltage buffer, it transfers the voltage. Current buffer transfers the current from one circuit to another circuit. Okay. Now we add another transistor here. We call it, let's Q3. Mm. So coming back to our basic current mirror circuit, and to that we add the another transistor Q3 between Q1 and the base of this, right? So see the connection, how this is connected. Okay. So now the IB and IB, in the 2 IB, the current here will be 2 IB, right? No, this is the emitter side and this is the base side. How much current will be here in the base?
IB.
In terms of this 2 IB?
IC is equal to alpha IE. Oh, sorry.
Let's call it IB3.
IB3. 3 is equal to IC is equal to IB. IC is equal to
So how much will be IB3?
IB by 1 plus beta.
Right. Okay. So now the IB3 here will be 2 IB divided by beta plus 1. So that's the emitter current, right? And that's the base current, right? And base current IB is IE divided by beta plus 1. So before IE, it was supplying the full of this base current to IB. Now it is not supplying this base current, but supplying only a fraction of this, right? Here it is supplying only the base current for Q3, and that is actually only fraction of this, what is needed. And most of the current is coming from here, right? Which will be 2 IB, right? Times alpha, right? That's the IC, alpha IE, right? So most of the current is basically supplied by Q3, right? And only a fraction will come from I in. So the I in will get much closer to IC1, and IC1 is IC2, which is equal to I out. So I in and I out will be now much closer, right? Gain will be much closer to 1, and error will be reduced. So now let's see what is the error with the new circuit. So now I in IC1 plus IB3. So that is IC1 plus IB3, and IB3 is 2 IB divided by beta plus 1, and IB is basically IC1 divided by beta, right? IC1 divided by beta. So IC1, when you take it out, you are left with here 2 by beta and beta plus 1. Okay. And IC1 is IC2, so replace IC1 by IC2, and here you have 2 slash beta plus 1, and IC2 is I out, so you have this Now the gain is I out by I in, and so here again 1 plus, okay, the corrections we need here. That will be 2 divided by beta times beta plus 1. So now this part you see, instead of 2 by beta, now 2 divided by beta times beta plus 1, that is much smaller. So gain will be much closer to 1, right? So it's less than 1, but it's still much closer to 1. And the error will be similarly, let's write the error here. So our actual gain is 1 over 1 plus 2 divided by beta times beta plus 1 minus the ideal gain, which is 1. And then after doing the math, you get this. So this part will be much, much smaller than 1. This is our beta squared. So we can always ignore that and approximate this to minus 2 divided by beta plus 1. Okay. So now our new error now with the modified circuit is minus 2 divided by beta times beta plus 1, which also we can express as minus 2 by beta square, right? Since beta is much larger than 1. Okay. Is that clear, guys?
Yes, sir.
So before the error was 2%, let's say minus 2 by beta. Now it's a square of the beta. So a significant reduction in the error, right? So if beta is, let's say, 100, right? So the error will be
So minus 0.02%.
yeah. In fraction, it will be 3, 0, and 2. And if you convert in percent, it will be 0.02%. Okay? So which is quite insignificant, right? We can live with that. Any question, guys?
No, sir.
Okay. So this circuit here is called the beta helper. So this one helps to reduce the error due to the finite beta. So that's why it's called the beta helper. And so these are modified current mirror circuit, right? To reduce the error due to finite beta. Okay, guys. So if you can come up with another solution to this, so there are other solutions, of course, but let's see if you can find some other solutions.
Sir, what about adding a MOSFET?
What?
Sir, MOSFET.
MOSFET, yeah, MOSFET, you don't have error due to finite beta because there is no the gate current is always zero. MOSFET, you have error only due to the finite output resistance. Yeah. Okay, guys. So today we don't have enough time to go to our next this part of this, the error due to finite output resistance. So that we will discuss in our next lecture. So we'll have, as we said in the last class, we'll take one extra class or makeup class tomorrow, right?
Yes, sir. Tomorrow at 12 p.m.
No, not 12 p.m. I have a meeting in the morning time. So we'll take it in the afternoon. We have a meeting. We'll take in the afternoon, 2 or 3, which one sounds good to you? 3 o'clock? 3 to 5 p.m. will be okay?
Okay, sir.
Hmm?
Okay, sir.
Okay. So we'll have our next class tomorrow from 3 to 5 p.m. Okay, guys, I'll see you tomorrow then. And that will be all for today. Stay well.
Can you extend the deadline of project?
Sorry,
Can you extend the deadline of the project 1 or 2 days?
what's the due date now?
26, I think.
26. 26 is Saturday.
Yes, sir.
Hmm. Okay, submit by 28 then.
Okay, sir. Thank you.
Okay.
Thank you, sir.
Thank you. And Allah Hafiz.
Allah Hafiz Tazammul.
Allah Hafiz, sir. Sorry.
আহমেদ ভাই কি অবস্থা?
রেকর্ড ব্যাক রেকর্ড হয় না?
ও আচ্ছা আচ্ছা, ঠিক আছে। আল্লাহ হাফেজ।